Hello, ladies and gentlemen. Welcome to the International Conference on Machine Learning and Automation 2023. I'm Wang from the University of Auckland. Today, I will be sharing with you an exciting and innovative topic. That is machine learning for intelligent biomedical data quantification. With the ever-increasing volume and complexity of biomedical data, the application of machine learning techniques has become paramount in unlocking the hidden potential within these datasets. As researchers, healthcare professionals, and technologists, we are constantly striving to improve patient outcomes and revolutionize the healthcare industry. By harnessing the power of machine learning, we can analyze vast amounts of biomedical data to identify patterns, correlations, and trends that may not be immediately apparent to human researchers. During this presentation, we will explore the diverse applications of machine learning in biomedical data analysis. So the content of my presentation includes three major parts, that is, medical imaging data analysis, image-guided intervention, as well as electrochemical sensor data analysis. For medical imaging data analysis, we know that medical imaging is playing a vital role in diagnosing and monitoring disease, generating large volumes of data. Machine learning techniques can analyze medical images to extract valuable information and insights. For example, machine learning algorithms can identify and classify anomalies or patterns in medical images. By leveraging machine learning and also deep learning algorithms, we can enhance the disease diagnosis, improve treatment planning, and enable more personalized patient care, and enable precision medicine. For image-guided intervention, we know that image-guided intervention basically refers to the utilization of real-time imaging data during the medical procedures to deliver precise and accurate interventions. Machine learning in this application can assist in making critical decisions during interventions and optimize the surgical outcomes. By analyzing the live imaging data, machine learning algorithms can provide real-time feedback and guidance to healthcare professionals. Incorporating machine learning into image-guided intervention can enhance the procedural accuracy, improve the patient safety, and minimize invasiveness. The third application is electrochemical sensor data analysis. Electrochemical sensors are powerful tools for detecting biomarkers and diseases. The machine learning techniques can also be applied in this application to analyze the data generated by sensors. By leveraging machine learning algorithms, we can improve the accuracy and the sensitivity of the disease detection. So the intelligent analysis of electrochemical sensor data utilizing machine learning enables the early diagnosis, personalized treatment, and also improve patient outcomes. Now let us first look at the infarct detection from DWI images. DWI is one commonly modality utilized for stroke patients. So the pipeline includes the following steps by applying the brain mass and also computer threshold and also some mathematical operation, for example, dilation and erosion. And we can derive a different image by comparing the original image and the image operated by morphological reconstruction. So finally, based on the difference image, a proper threshold will be applied and obtain the impact. This is the traditional image analysis pipeline. The advantage of the traditional image analysis pipeline is that we don't require a large amount of the training data. Just based on this kind of processing steps, we still can obtain the reliable segmentation of the impact. With the fast development of machine learning and deep learning, we developed an advanced automatic segmentation pipeline for delineating the cerebral microbleed from SWR images. The SWR image is also one MRI modality, which is very sensitive to detect the cerebral microbleeds. By applying the deep learning algorithm, we can firstly identify the possible candidates as shown in the squares in the left figure, the right square. Then within these candidates, we apply the support vector machine to further classify what kind of candidates are real cerebral microbleeds. Then the accuracy can be further improved. The experimental results demonstrated that our automatic pipeline based on machine learning can achieve the high sensitivity of 89%. This is the application for applying machine learning algorithm to develop the quantification for tumor sphere migration utilizing machine learning based algorithm and also some finite element analysis. In the left figure, the predict the boundary segmentation as shown in the third column is the predict the boundary segmentation from the trained UNet model. The results show that the automatic boundary segmentation is quite consistent with the manual boundary segmentation. Based on the segmentation result, the migration analysis can be obtained. For example, the figure A, the raw images of the migrating tumor sphere over the course of 24 hours. With the sub-figure B on the right side, we generate some mesh models from the segmented image and also display the migration mechanism of each element as the mesh deforms over time. The subfigure C shows the mean of the migration magnitude from all the boundary elements, and which can be used to investigate the overall migration magnitude over time. The subfigure D is the radar chart containing points that represent the mean migration magnitudes of the boundary elements. So the prior knowledge in medical domain can be incorporated into the brain atlas. So the brain atlas is very helpful to derive some clinical scores. For example, in this slide, the atlas of aspect, which is Alberta Stoke Program Early CT score, is normally utilized for CT images. So we developed a version of aspect atlas for MR data. So the advantage of the MR atlas is that it can has a strong and reliable registration capability to map the individual MRI data with the brain template for MRI and also the corresponding aspect atlas. It means that just based on the individual MRI data and also the aspect MR atlas, we still can derive the aspect score reliably and also automatically based on the intelligent machine learning based lesion segmentation that maps the individual lesion to this aspect atlas. They still can obtain the aspect score automatically. Another atlas I want to share with you is the recently developed hybrid atlas, which is utilized for stroke recovery prediction, especially for the motor recovery prediction. This atlas contains motor regions, as well as the motor-associated white matter tracks. It means that this atlas is more comprehensive. It includes the information from the cortex and also the information from the white matter fiber tracks. So this kind of atlas can be more readily to be utilized to predict stroke outcomes in the aspect of the motor capability. The visualization techniques can also be helpful for the diagnosis by applying the machine learning algorithm to align the different modalities. So we call this kind of multiple modality image visualization called medical image fusion. For example, in this example of medical image fusion, on the left side, the lesion of the infant can only be displayed in this FLAIR image or T2 image, while for the vascular structure, originally it's difficult to identify the lesion. So we can only see the vascular structure. So by applying the medical image registration and the medical image fusion, we can artificially to put the lesion in the vessel image, as shown on the figure of the right side. So by this kind of integrated visualization, the clinicians can visualize the relationship clearly between the lesion and also the vascular structure, which can improve a lot of accuracy and also convenience for the diagnosis. Machine learning can also be applied to derive computational fluid dynamic simulation metrics. For example, based on the personalized aneurysm, intracranial aneurysm morphometry, which can be segmented from the CT images, we can obtain the morphometry, then we can perform the computational fluid dynamic simulation to derive the important metrics, such as the speed and also the shear stress. So the machine learning algorithm or deep learning based algorithm can be applied in this kind of simulations. The advantage of a deep learning based simulation is that it can reduce a lot of computational costs and also derive quite a bunch of parameters within very short time. This slide demonstrates our recent development for the optimal design of a recoil for multi-target magnetic brain stimulation. The traditional TMS, transcranial magnetic stimulation, contains only one coil, and also there is only one focal target during the treatment. So this design of a recoil has the advantage of delivering multi-targets, a multifocal point for the brain stimulation. So the basic mathematical model for the multi-target magnetic brain stimulation is based on the temporal interference. Our simulation results demonstrate that it's very feasible based on the temporal interference. So by applying, for example, 3 coils in different coordinates, we can generate different kind of focal points as we expected. It means that the design of a recoil for multiple focus stimulation is very feasible. So this kind of stimulation demonstrates that it's very potential to deliver more personalized and more diverse brain stimulation. Camera-guided navigation is also very useful for the intervention. For example, our TMS treatment, we can incorporate the personalized image. It can be CT and MRI, and we can also incorporate the brain champion and atlas to improve the stimulation accuracy. This kind of image-based planning can be applied to the real patient by applying image-guided navigation. So by using the tracking system, it can be the optical tracking system or magnetic tracking system. The pre-intervention plan can be reliably adapted to real-time stimulation for the patients. The synthetic MRI generation is another application for applying deep learning to generate pseudo images based on some other modalities. For example, in this slide, we train a deep learning model to generate synthetic brain MRI from CT images. So different kind of deep learning models, for example, cyclogram, pixel to pixel, and the pair the cyclogram has been trained, and we can see that it's highly potential that the synthetic MRI can be generated from the CT images. So the deep learning can also be applied to improve the registration accuracy by generating the image and painted images. For example, as shown in this slide, for the stroke patient, the registration of individual patient data, for example, MRI image, so the standard brain template can be challenging, especially for the patient with a large stroke lesions. So we propose to, before applying registration, we first perform the lesion segmentation as shown in the mid column. After that, we perform image imprinting to fill in the normal tissue in the regions of lesion. Then, if we apply the imprinted MRI for the registration with the brain template and atlas, for example, the ICBM template, we can see that the imprinted MRI achieved much better and much higher registration accuracy in comparison with the registration of original MRI with stroke lesion, especially for the patient with a large. The structural and the function relationship of the cortical motor system only after stroke is our recent development based on the machine learning. Our objective is to utilize medical imaging biomarkers to replace the biomarkers delivered by transcranial magnetic stimulation. So support vector machine model was trained based on the features from T1 and TTI. So our machine learning model can achieve the proceed of 81%. It means that the multivariate MR approach based on the machine learning across the multiple tracks actually has the potential to yield more information than univariate biomarker analysis shown in the paper published recently. Regarding biosensor data analysis, I want to briefly share with you two applications. One is anomaly detection for electrochemical sensor data analysis. As shown in this figure, you can see that there is some differences between the normal and abnormal signals. For example, subfigure A shows a signal with normal sensory behavior, but it's highly common that the signals would contain some abnormal endpoints. For example, as shown in subfigure B, or presented there are some abnormal time interval as shown in the subfigure C and D. So our objective is to automatically perform this kind of anomaly detection before we sending the signal, the data to for the automatic quantification. So this is our anomaly detection pipeline by firstly applying some pre-processing, then and also some data augmentation methods. We divide the data into training and testing. And then one autoencoder prediction model is trained based on the training data set. Then we can perform the reconstruction for the data. Then we can calculate the difference between the reconstructed data and original data. So we can obtain some error, for example, reconstruct error in terms of a mean square error. Then we can compare the MSE with some threshold. The threshold can be determined using the TDE. So then we can further decide if the MSE is larger than one threshold, then we can see, okay, it is abnormal. This is the basic pipeline for the anomaly detection. Our experimental result show that the accuracy can be as high as 80%, and the performance of vanilla and the integrated models were comparable, and also the LSTM-based autoencoded model that shows the least accuracy, and the integrated models of ULSTM and vanilla autoencoder, the accuracy can be as high as 80%. So basically, the anomaly detection is very feasible based on machine learning data. So the second application is to predict and analyze the concentration from the electrochemical sensor data. So we proposed some data augmentation method. This is our data augmentation method. By applying different weights on the existing signals, we can generate new data. So this kind of method is very effective by generating a lot of new data. This is our machine learning model for the prediction of the concentration. So basically, the structure is about the long short-term memory. But regarding the LST model, there could be different optimization options, for example, optimizers, hidden units, and other options regarding the original data augmentation. So this is our model evaluation results, including the original signals and also the augmented signals. Basically, the data augmentation is very effective to increase the predicted performance from the experimental results. And the LSTM can automatically detect the analyzed concentration from the sensor signals, especially for the bilateral or BLSTM model, which is more suitable for the longer term series. So throughout this presentation, we have explored the applications of machine learning in three key areas of biomedical data analysis: medical imaging data analysis, image-guided intervention, and electrochemical evidence sensor data analysis. So machine learning enables us to extract meaningful insights from complex biomedical datasets, improving disease diagnosis, treatment planning, and patient care. However, as we embrace this technology, it is essential to address ethical consideration and ensure responsible implementation. In conclusion, the intelligent analysis of biomedical data utilizing machine learning holds tremendous potential for advancing healthcare and transforming patient outcomes. So let's continue to explore and innovate in this field to create a future where data-driven insights and advanced technologies converge for the betterment of human health. Finally, I want to acknowledge my collaborators as shown in this slide. That's all for my presentation. Thank you.